Hello everyone, welcome back to the very last video review of Calculus 112, or in other words, Calculus 2 final exam. So this is the very last video I'm making about any sort of review for any class for this semester. So we have 11 questions covering most of the Calculus 2 curriculum. Of course, we're going to skip some topics. I think it's just one question that I'm skipping, or two questions, because the mathematics department has decided that certain topics will not be on the exam, like applications to Taylor's series. We don't have anything like conditional convergence for series. We also don't have the length of parametric curves. Okay, we don't have to have arc length. We don't have to find the surface area of volumes of revolution. So the exam is boiled down to the very basics of each chapter, really. So it should be pretty easy. It should be a breeze to go through these questions. And I wish you the best of luck on Wednesday's exam. I'm pretty sure you all will do fine because you're all very smart people. All right, so let's start off by doing this very cute integral from 0 to pi over 4 of x sine of 2x dx. For this type of integrals, when you have the product of two or more functions, the first thing that has to come to your mind is integration by parts. So we're going to let our u equal to x, right? Because when we differentiate our x, at some point we're going to get 0. And then we're going to let v equals to sine 2x dx, right? That's going to be dv. And so if we integrate dv, we're going to get that v is equal to the integral of sine of 2x dx. And what's the integral of sine? Well, if you remember the unit circle trick, we have the values of sine x over here, the positive sine x, negative sine x is over here, cosine x, and negative cosine x, right? So if we differentiate, we're going to move clockwise in this direction. So if we differentiate once, we go from sine to cosine, and if we integrate, right, we go from cosine to sine, and so on. So this is a pretty cool trick to just remember on your exam, so that you don't have to rely on just pure memorization. And so over here, we're going to get that the integral of sine is negative cosine, but of course, we're going to use the chain rule, right? We're going to have negative 1/2 cosine of 2x. Okay, so this is our v, and of course, our du is just dx. So we're going to have that the indefinite integral of x sine of 2x dx, okay, that's all equal to u times v, which is negative x over 2 cosine of 2x, and then we're going to subtract the integral of v du. So we're going to put minus, and then we're going to integrate v times du, which is dx. So that's going to be negative 1/2 cosine of 2x times dx, right? Okay, so this negative and this negative become positive, right? And we're going to have the integral of 1/2 cosine 2x. Of course, the integral of cosine x is sine x. But of course, we have to use the chain rule. So this is nothing but, the integral of x sine 2x is nothing but negative x over 2 cosine of 2x. Okay, and then we're going to have 1/2 over 2, which is 1/4 of sine 2x. Okay, plus c. But of course, we're going to find the definite integral from 0 to pi over 4. So all we had to do is take this indefinite antiderivative and just plug in the lower and upper limits. So we're going to have the integral from 0 to pi over 4 of x sine of 2x dx is nothing but negative x over 2 cosine of 2x, right, plus 1/4 sine 2x. And all of this is going from 0 to pi over 4. Okay? Very simple, right? Now we have to substitute our values for the upper limit. Okay, over here, values of x. So this is nothing but negative pi over 4 over 2, which is 4 times 2 is 8. So pi over 8 cosine of 2 times pi over 4 is nothing but cosine of pi over 2, which is 0. So this cancels out. And then we're going to have plus 1/4 sine of 2 times pi over 4, which is nothing but sine of pi over 2. And of course, sine of pi over 2 is 1, right? So this is going to be 1, right? And then we're going to subtract the lower limit value. And you know, we can already see what's going to happen. So 0 times anything, right, is 0, except for infinity. In that case, you're going to have an indeterminate form. But of course, this is cosine of 0, which is 1, times 0 is 0. And then sine of 0 is 0. So all we have left is 1/4. So 1/4 is the answer, 1/4. Okay, so integration by parts is not too bad. It's important to know when to use it, okay, when to recognize that the problem is asking for integration by parts, right? So when you have the product of 2 or more functions. All right. So that's question 1, part A, and now we're going to do part B. So for question 1, part B, we have the integral of x squared divided by 4 minus x squared, all of this to the power of 5/2 dx. Okay, and so for this problem, you know, the first thing I tried was use substitution. You know, let's say what happens when u equals 4 minus x squared, but you know, when you take the u and then you take into account that you have x squared on top, it's not going to work very nicely. So what type of integration technique should we use in here? Well, clearly on the bottom we have 4 minus x squared, right? And that sounds familiar to, you know, trigonometric identities. If we think about the trig identity of a minus a, right, sine squared of theta equals to cosine squared of theta times a, okay, we can take advantage of that trigonometric identity and then, you know, manipulate this expression algebraically so that we can integrate it easily in terms of trig functions. So in order to get it in this form, we're going to have to say that a, well, a is going to be 4, but of course we will rather say that a is 2, right? Because it's going to be 2 squared. So in fact, it should be a squared. Yeah, that should be the right form. But you know, we're just going to take advantage of that. So how about if we have in here, instead of this x squared, we have 4 sine squared, right? We can factor out the 4 and then we get 4 cosine squared theta. So we're going to do the following. We're going to let, okay, x equals to 2 sine theta, right? Because when you, what happens when you square this? When you square this, you get x squared is equal to 4 sine theta, square theta. And you can take advantage of this in order to, okay, factor this out and just make it one term in the denominator. Okay, now dx, over here, dx is nothing but the derivative of 2 sine theta, which is 2 cos theta, d theta. All right, so now all we got to do is substitute our values in the integral. So we have the integral of x squared, which is 4 sine squared theta, and dx is 2 cosine theta d theta. All of that is going to be divided by 4 minus x squared, which is nothing but 4 sine squared theta. All of this to the power of 5/2. Okay, so this is going to be, you know, simplified very nicely. We're going to factor out a 4 over here. So this is nothing but the integral of, let's factor out the 4 times 2, which is 8, outside of the integral. And then we have sine squared of theta, cosine theta, d theta. All of that divided by, factor out a 4, raise it to the power of 5/2. You're going to get that 4 rooted, right? 4 square root of 4 is 2. 2 to the power of 5, okay, is going to be 32. So we have 32 over here. And then we're going to have 1 minus sine squared theta to the power of 5/2. Okay? This over here is going to become cosine squared theta, right? And look at that. Cosine over cosine squared theta, well, it's just 1 over cosine theta. And of course, 8 over 32 is just 1/4, right? Because 8 times 4 is 32, so it's 1/4 integral of sine squared theta divided by cosine theta, okay, d theta. But of course, I forgot that we were raising this to the power of 5/2, right? So we're going to have cosine squared, right? we're going to take the square root of cosine squared, so that's actually just cosine theta, right? And then raised to the power of 5, that's cosine to the 5th power. And cosine to the 1st over cosine to the 5th, well, it's going to get you to 1 over cosine to the 4th. So this is actually cosine to the 4th power of theta. Okay? Now, what can we use here? What, can we substitute this? Can we maybe change the form a little bit so that it's not going to be, it's going to be convenient for us? Because, right now it doesn't seem like it's easy to, integrate. But of course, we can change this a little bit. We can change it to 1/4 of integral sine squared over cosine squared is tangent squared, right? So it's tangent squared theta. And then we're left with 1 over cosine squared theta, which is nothing but secant squared theta. So these integrals, trigonometric integrals, very common to see. So how can we make a substitution over here? Well, we know that if we have tangent squared, right? Or no, just tangent theta, right? And then we take the derivative of tangent, right? The derivative with respect to theta, we're going to get secant squared theta, d theta, right? So over here, we got a secant squared theta, d theta. And we got a tangent squared. So how about we make the substitution? We're going to make the substitution u is equal to tangent theta such that du is equal to secant squared theta, d theta. See? Now it's way easier to do it. So we're going to have 1/4 integral of u squared du, right? This is nothing but u cubed over 12 plus c. Now we substitute back our u. We know that u is tangent theta. So that's going to be tangent cubed theta divided by 12 plus c. But of course, theta has a value. Okay, theta has a value. Or let's do this, from the beginning. Because we know that x equals 2 sine theta, right? So if we change this a little bit, we know that sine theta, right, from this equation over here, is equal to x over 2. And this is nothing but the description of a triangle. So we have the angle theta over here, and then we know that the angle the opposite side to it is nothing but x, and the hypotenuse is 2. And we can infer that, therefore, this is the square root of 4 minus x squared, right, by the Pythagorean theorem. And we can find any trigonometric function based on this triangle, since we got this relationship. Tangent of theta, well, it's just opposite over adjacent, right? So that means that this is nothing but the opposite side divided by the adjacent side, which is the square root of 4 minus x squared, right? We can substitute back in there. So we have that the integral of x squared divided by 4 minus x squared, right, to the power of 5/2 dx is nothing but tangent cubed, which in this case is this value over here cubed. So that's just going to be x divided by the square root of 4 minus x squared, right, to the power of 3 divided by 12 plus c. Okay, you can change this to make it look nice if you want. You could do like, I don't know, x cubed over 4 minus x squared to the power of 3/2 maybe times 12. You could do it like that, plus c, of course. Don't forget plus c. If you forget plus c, you're going to get a lot of points off on the exam. So this is the answer to this problem. Pretty trivial, right? Not too hard. I'm sure you're going to do it on the exam pretty easily if you remember these techniques. Now, let's do the next problem. Problem number 2, part A. Okay, so for problem number 2, part A, we got the integral of x minus 4, all of that divided by x cubed plus 4x dx. And of course, this is a rational function over here. We don't like rational functions very much, right? We don't empathize with them. So we're going to do, partial fraction decomposition in here to destroy this bad boy. So we're going to have that x minus 4 is nothing but, okay, all of this divided by x cubed plus 4x, okay, is nothing but x minus 4 divided by x times x squared plus 4, right? We're going to factor out an x on the bottom. And then we can do some partial fraction decomposition. So we're going to let, a, this is going to be equal to a over x, right? We're going to split this up into two different fractions. So a over x plus bx, right? We were accounting for the fact that this factor over here is a square factor, is a polynomial of second degree. So we have bx plus c divided by x squared plus 4. Okay, now we can find the least common denominator over here, and then we can solve for a, b, c. Okay, so we have that x minus 4 is equal to a times x squared plus 4, right? And then we have plus bx, right, plus c, all of that times x. So we're going to factor each term, okay, term by term. So we have that a plus b, all of this times x squared, okay? And then, well, if we don't have a square factor over here, we can just say that this over here is equal to 0, right? So we have that a plus b is equal to 0. Okay, so that's our first equation to find the solutions to these three variables. Three constants, really, they are constants. Now, we also have that, we have a 4a over here. We don't have, anything else that has the 0th power, okay, factor. So we're just going to have that 4a is equal to this over here, which is negative 4, which means that a is equal to negative 1, right? We also have that cx, right? We have a cx over here, and that's about it, right? We only have a cx. And of course, the x, the first power constant is 1, so that means that c has to be equal to 1, right? Now, we know that a is negative 1 and a plus b is 0, which means that b is equal to 1. Okay, so we have these three constants. So we can go ahead and substitute that in there. So we have that this is nothing but the integral of a, which is negative 1, divided by x. And then we have b, so plus bx, and then c is 1, so plus 1. Okay, very nice. So now what we're going to do, oh, and all of this, b is 1. Yeah, my apologies. That's just 1. So 1x plus 1. And then we have all of this divided by x squared plus 4 dx. All right, so all we got to do here is just integrate this. So the integral of negative 1 over x is just negative ln absolute value of x, right? And then over here, we're going to split this up into two different integrals. We're going to split it up into the integral of x over x squared plus 4 dx and the integral of 1 over x squared plus 4 dx. Okay, this integral over here is very easy to do. We're going to let u equal to x squared plus 4 such that du is 2x dx. We have an x dx in top, so we just divide du by 2, which means that this is nothing but 1/2 ln absolute value of x squared plus 4. Okay, so this is our second value, so we have negative ln of x plus this. And then this integral over here is a basic integral. This is nothing but, 1/2 tangent inverse. Yeah, actually, let me write it as arctangent. Yeah, that's better. Arctangent of x divided by 2. All of this added with c. So this is going to be the value of this indefinite integral. And of course, don't forget plus c because you might get points off. All right, so that was a breeze. Now let's do part B. All right, so for part B, we have the integral of x dx divided by 9 plus x squared, all of that to the power of 3/2. Okay, now this one is actually very easy, even though it looks intimidating. So all we gotta do is take into account that the bottom factor, okay, the bottom term in the denominator is nothing but a square factor. It's a second degree polynomial, and the numerator, of course, is a linear factor. So that just tells us that a u substitution is probably the best to do. So we're going to let u equals to 9 plus x squared, right? Such that, okay, du is equal to 2x dx. And of course we have an x dx on top. So we can say that du over 2 is equal to x dx, okay? So we make these substitutions, and we have that this is 1/2 integral of du over u to the power of 3/2, okay? And this is nothing but 1/2 integral of u to the negative 3/2 du. We add 1 to the exponent, which is 2 over 2. So we're going to get negative 1/2. So that's going to be 1/2 times u to the negative 1/2, of course, divided by the exponent, which is nothing but multiplied by negative 2. And the 2 cancels out, so we have, negative 1 over u to the 1/2. And of course, u is going to be 9 plus x squared, so we substitute this and we get negative 1 over 9 plus x squared, okay, and then this is the square root of that, plus c, don't forget plus c. That's the indefinite integral. Okay, now let's do question number 3. So for question 3, okay, we're going to have to find, okay, we're going to evaluate these integrals if they are convergent, okay, or show that they are divergent. Okay, so these are basically improper integrals. So these are improper integrals. Okay, so the first integral is the integral from 0 to 1 of x ln of x dx. Okay, so of course we have the product of two functions, so that sounds like we're going to use integration by parts, right? Taking advantage of the fact that x, when you differentiate it, gets to 0. But of course in this case it's actually very different because you always want to find a way so that your dv is easy to integrate. And of course ln of x is not very easy to integrate. It's a two-step problem. So we'll rather say that u is going to be ln of x and dv is dx, and it's for a reason, right? Because differentiating ln of x is way easier than integrating it. So we're going to say solve the indefinite integral of x ln x dx first, right? So of course we can say that u is x, but it's going to make it too complicated. So let's let u equals to ln of x. And dv is going to be x dx, right? Which means that du is going to be the derivative of ln of x, which is 1 over x dx. And the integral of x, well, it's just x squared over 2. Okay, so we're going to use integration by parts over here. So we have that the integral, okay, of x ln x dx is nothing but u times v. And of course, u in this case is going to be ln of x, and v is x squared over 2. So it's going to be x squared over 2 ln of x, right? And then we're going to subtract the integral of v du. So v is going to be x squared over 2, and du is 1 over x dx. So look at that. This cancels out, and we have the integral of x over 2 dx. It's very easy to do. So this is nothing but x squared over 2 ln of x, and then minus x squared divided by 4, right? Plus c. So this is our indefinite integral. But of course, we're going to find the definite integral, the definite improper integral of this function from 0 to 1. So of course, don't forget to use limits for improper integrals. It's mathematical standard form. So we're going to use this to our advantage that we already know, the indefinite integral. So we're going to say that integral from 0 to 1 of x ln of x dx is nothing but the limit, okay, as over here we're going to find out for which limit, right, the lower or the upper limit, the lower or the upper bound, is this function undefined. And of course, ln of 0 does not exist, or well, the limit as it goes to 0 is just going to be a negative infinity, so it's not determined. It's not determined at that point. So we're going to say that this is going to be the limit as a, okay, approaches 0 from the right, okay, because the function of ln of x, right, the function ln of x goes like this, right? So it has no negative values, right? Ln of x has no negative values, so it's approaching 0, okay, the value of x equals 0 from the right, not from the left. So we have to specify this in our limit. So it's going to be the limit as a goes from to 0 from the right of the integral from a to 1 of x ln of x dx. And we know the indefinite integral, so this is going to be the limit as a goes to 0 from the right of this indefinite integral, right, this antiderivative, which is x squared over 2 ln of x minus x squared over 4, evaluated from a to 1. Okay, we just substitute our values. So we have to substitute the upper limit over here. Since it's 1, we're going to have 1/2 times ln of 1, which is 0, right, minus 1/4. So let's put that in here. So we're going to have the limit as a goes to 0 from the right of negative 1/4, right, negative 1/4 minus, okay, this limit, of course, the same thing evaluated at a. So we're going to have a squared over 2 ln of a, right? And of course, this should be in absolute value, but it doesn't really matter. So it's just ln of a minus a squared over 4. Okay, this is going to be our limit that we have to evaluate over here. So we have some work to do. So this is nothing but, okay, negative 1/4 minus or plus the limit, okay, as a goes to 0 from the right of, a squared over 4 minus a squared over 2 ln of a. Now this over here is just going to 0, right? When we substitute a as 0, this term will go to 0, but this term not quite, because we're going to get something that will be 0 times infinity, which is an indeterminate form. But it's not in the L'Hopital case, so we want to make it in such a way that it's infinity over infinity or 0 over 0. Either way works, so we have to manipulate this expression algebraically in such a way that we could get infinity over infinity when we substitute directly, or 0 over 0. So either way works. Now, okay, this is nothing but 1/4 plus the limit, or no, let's put the minus. Let's just take the minus outside. Limit as a goes to 0 from the right of a squared over 2 ln of a. And over here, this we can use the fact that we can divide by a squared on top and bottom, right? So this limit will be nothing but the limit, okay, as a goes to 0 from the right, okay, of, if we divide top and bottom by a squared, right, using this trick, we're going to get ln of a divided by, okay, 2 over a squared. Okay, and now when we substitute this by 0, we're going to get, ln of 0 from the right. That's negative infinity, right? So that's negative infinity, and then divided by 2 over a squared. And 2, when we substitute 0 into a, we're going to get 2 over 0, which is infinity. So we got infinity over infinity, which means we can apply L'Hopital's rule. So that we're going to take the derivative of the top and the bottom, and then we're going to take the limit of that. So we have this, this is this limit, okay? We're just focusing on that limit. The limit of a squared ln of a divided by 2, okay? As a goes to 0, it's nothing but the derivative of this over this, right? So that's going to be the derivative of ln of a, which is 1 over a, divided by the derivative of 2 over a squared. So that's going to be, okay, if you bring the a on top, that's a to the negative second power. So that's going to be 2 times negative 2, which is negative 4, right? Negative 4, a, okay, to the negative third power. All right, as a goes to 0 from the right. Okay, so if we bring this to the top, okay, because this is basically, 1 over negative 4 over a cubed. We can bring it to the top, and so we're going to have nothing but the limit as a goes to 0 from the right of a cubed over negative 4a, right? And this cancels out, so we have the limit as a goes to 0 from the right of a squared over negative 4. And well, that's just 0, right? 0 over negative 4 is 0, so the limit is just 0, okay? So this is 0, and we're left with 1/4. So 1/4 is the answer, okay? All right, that was an interesting problem. All right, so for question 3b, we still have an improper integral, and that's going to be the integral from 1 to infinity, okay, of x times e to the negative x squared dx. Okay, so we're going to evaluate that integral by integration by parts. Okay, so this is an improper integral. So let's find the indefinite integral, right? The indefinite integral of x e to the negative x squared dx. All right, so we have to use integration by parts because it's a product of two functions. But I mean, you know, you could argue that, you know, it's not necessary because as you can see, this power over here is negative x squared, and we have the function over here x, the linear function, and then we have a square function. So we could use a u substitution. How about we let u equals to negative x squared, right? So that du is going to be negative 2x dx. And we got a x dx in here. So we can you know, use that. So we have that negative du is going to be x dx. Okay, negative du over 2 will be x dx. So we substitute this in here, and we have that this is nothing but the integral of, okay, e to the u times du, okay, and then times negative 1/2. So this over here will be the integral using u substitution. Okay, so this is nothing but negative 1/2 e to the u plus c, right? This is the indefinite integral, and of course if we substitute u back into whatever u is, which is negative x squared, well, we have that this is negative 1/2 e to the negative x squared plus c. This is the indefinite integral, but of course we're going to find the improper integral from 1 to infinity. So we have to take the limit. So this is the limit as, okay, in this case at infinity is not defined, right? It's indeterminate. So this is as b goes to infinity of the integral from 1, right? From 1 to b of x e to the negative x squared dx. And of course we already found the indefinite integral, so we can take advantage of that. And this is the limit as b goes to infinity of this indefinite integral. So of negative 1/2 e to the negative x squared, okay, from 1 to b. So we substitute our values, upper and lower bound. We have that this is the limit as b goes to infinity of negative 1/2 e to the negative b squared, right? And then we're going to subtract, okay, negative 1/2 of e to the negative 1 power. Okay. All right. So over here we have to evaluate this limit to see what happens. And of course, you know, this is going to be, if we focus on that limit, this is the limit as b goes to infinity of negative 1 over 2 e to the b squared, right? And what happens when the denominator goes to infinity? Well, this whole expression goes to 0, right? So this goes to 0. Okay, this goes to 0. And we're left with the positive of this. So this is going to be 1/2 e to the negative 1, or 1 over 2e. Very nice number. Okay, so that's this indefinite integral. This improper integral, I mean. Let's go to the next question. All right, so for question 4, we're going to find the volume of the solid obtained by revolving the region and enclosed by y is equal to 1 over x squared plus x. So we got the function y is equal to 1 over x squared plus x, right? And we also got y is equal to 0. We got these limits. We got y equals to 0. We got x equals 1 and x equals 2, of course, and the y-axis, the x-axis, okay, which is basically the axis of rotation in this case. All right, so we're going to revolve this function about the x-axis. We're going to find the volume, okay, of this solid that is going to be generated. And of course, 1 over x squared plus x is a function that can be compared to, say, we can compare this to 1 over x squared, right? So we can say that the function is going to look like something like this. Look, it's going to fall from infinity, right? Because the limit of this function as x goes to 0 is very big, right? So that's going to fall from infinity, and then as x grows larger, well, y grows smaller. Well, falls to 0, right? The limit as it goes to infinity falls to 0. So this is what the function is going to look like, right? But of course, we're going to revolve this about the x-axis from 1 to 2. So this over here is going to be x equals 1, and this over here is going to be x equals 2. All right, so this over here will be the volume, okay? This will be the solid generated, right, when we revolve this. Okay, so this will be the solid, the volume of revolution. Okay, so remember that in order to find the volume of revolution, okay, given the function, the value of the function, this over here will be the radius r, right? And of course, the radius is changing with respect to the function, right? As it goes bigger, well, as x goes from 1 to 2, r is going to get smaller, right? With respect to the function. So we're going to use the function in our equation, right? And of course, remember that we're going to add up infinitesimal disks with radius, the value of the function. And of course, the thickness of the infinitesimal disk is going to be an infinitesimal quantity, dx. So we have that the area of a circle is equal to pi times the radius squared, right? But of course, that's only a circle. It's a two-dimensional figure. But a disk is a three-dimensional figure, in fact, because it has 3 dimensions. So this is going to be that the volume of this infinitesimal disk, right, of this disk that's very small, very thin, but large area, right, is going to be the area of one disk, right, with respect to the function r. So it's going to be pi and then r, right? But this is the infinitesimal disk, dv, right? This is the infinitesimal disk, and then this is the function r of x with respect to the variable x squared, pi r squared, right? Multiplied by the infinitesimal thickness dx, right? So to find the entire volume, we have to integrate this on both sides. And so we get that the volume of the disk is nothing but the integral, pi times the integral of the radius function, okay, squared dx. And of course, the radius is defined by the function 1 over x squared plus x. So we're going to square that function, and we're going to integrate it with the product of pi. So the volume of revolution will be pi times the integral, okay, from here to here, right, from 1 to 2 of this function, 1 over x squared plus x dx, right, and this is going to be squared. But, don't try to square this just yet, because there's an easier way to solve this problem from the beginning. So what we want to do is we want to split this function into the, sum of partial fractions. So let's split 1 over x squared plus x. Okay, we're going to factor it, and this is nothing but x times x plus 1. Okay, if we use partial fraction decomposition, this is going to be a, some constant a over x, plus some constant b over x plus 1. So we're going to find the least common denominator, and we have that 1 is equal to a times x plus 1 plus bx, which means that we have 1a plus 1b, okay, multiplied by x, plus, okay, a. All of this is equal to 1. So that means that a plus b is equal to 0, since on the other side of the equation there is no first degree function. There's not an x squared. There's not an x to the first power. And of course, this a over here will be equal to the value of this constant, 1. So if a is 1, b is negative 1. So we found our constants. So we can rewrite this function as 1 over x minus 1 over x plus 1. Okay? Now we're going to plug that in here. We're going to square it, right? So we're going to have that the volume is pi times the integral from 1 to 2 of this squared. So what happens when we square this, right? What happens when we square this? Well, we have the first term squared, right? It's going to be in the term in the form of a squared plus 2ab plus b squared, given that this is b and this is a, right? We're going to have 1 over x squared over here. When we square this, we're going to have 1 over x squared plus 2ab, which is going to be minus 2 times 1 over x times 1 over x plus 1, right? And then we're going to have plus b squared, which is going to be 1 over x plus 1 squared, okay? We're going to put this inside of our integral, so that's going to give you 1 over x squared, and then minus 2 over x times x plus 1, and then plus 1 over x plus 1 squared dx. So as you can see over here, we have a recursive fraction, because we can split this up again into whatever terms those are. So let's try splitting this up again. So this is basically, this is pi times the integral from 1 to 2 of 1 over x squared, right? And then this is basically negative 2 multiplied by this whole thing again. So we can rewrite it, okay? So this is going to be minus 2 times, the one function that we broke into 2 different fractions, right? Without squaring it, which is going to be 1 over x, right, minus 1 over x plus 1. And then we're going to add 1 over x plus 1 squared. All right, so look at this. We can already, solve this. This is nothing but, okay, pi, okay, times the integral of 1 over x squared. Well, that's just negative 1 over x. The integral of negative 2 over x is negative 2 ln, okay, absolute value of x. And the integral of negative 2 times negative 1, which is 2 over x plus 1, well, that's just going to be plus 2 natural logarithm absolute value of x plus 1. And over here we have plus the integral of 1 over x plus 1 squared. We use substitution, and you're going to get minus 1 over x plus 1. Evaluated from 1 to 2. Of course, this is multiplied by pi. Don't forget the pi. I tend to forget that. All right, so let's see what we get from this. So let me erase this. Okay, so this is nothing but, the volume is nothing but pi, okay? We're going to substitute 2 first, right? So this over here will be negative 1/2, okay, minus 2 ln 2, and then plus 2 ln of 3, and then minus 1 over 3, right? And then we're going to subtract. Let me erase this. We're going to subtract the same function evaluated at 1. Negative 1 over 1, right? That's just negative 1. And then ln of 1 is 0. ln of 2, so we have plus 2. I'm sorry, ln of 1 plus 1 is 2. So ln of 2 minus 1/2, okay? So let's see what we can cancel out from this. Okay, we have negative 1/2 minus 1/2, so that's going to be negative times negative is positive, so that cancels out. Okay, we have negative 2 ln of 2, we have minus 2 ln of 2, so that's going to be 4 ln of 2. So we have that the volume is pi times 4 ln of 2, and then we have 2 ln 3, right, minus 1/3, minus 1, right? So this is negative 1, plus 1, which will be, it will become plus 1. This is a negative, right? Negative 2 minus 2 is 4. and this is going to be plus 1, which is 3 over 3. So 3 minus 1 is 2. So it's plus 2/3, right? And then we're going to have plus 2 and then 3. Okay. All right. So I think this is it. This is the answer in simplest form. If you want to expand this number, pi, okay, you can do that, but that's fine. This is an acceptable answer. Or you could also combine these terms. I don't know how that looks like. I mean, let's see. This is pi times, okay, this is 3 to the second power is 9. So that's ln of 9 minus ln of 2 to the fourth power, right? Which is going to be 2 times 2 is 4, times 2 is 8, times 2 is 16. Okay, and then plus 2/3. We can use logarithmic rules, and then we're going to have pi times ln of 9 over 16 plus 2/3. It's a little bit more compact. I mean, it's the same answer, so it doesn't matter. Okay, so that's question 4. All right, so for question 5, which is in regards to parametric equations, I'm only going to do part A because part B has to do with the length of the parametric curve, which is not going to be on the exam. Okay, so for question 5a, we're going to consider the parametric curve given by x of t is equal to e to the 3t divided by 3, and then y of t is going to be e to the 2t over 2. Okay, so we're going to find dy dx, okay, and d squared y over dx squared, which is the second derivative of the function y. All right, so remember that to find the derivative dy over dx, okay, we just use the chain rule. So we have that this is nothing but dy, okay, over dt times dx, times dt, right, because this really isn't doing anything, right? dt over dt is 1, so divided by dx. Okay, so if we rearrange this a little bit, we can say that this is nothing but dy over dt, okay, times dx dt to the power of -1. So we can bring it down, and we have that this is dy dt over dx dt. So you just gotta find the first derivative with respect to t of each function, x and y. So we have to find dy dt. So the derivative of e to the 2t, okay, so it's d e to the 2t, okay, over 2 dt. Let me put the dt on the bottom. All of that divided by dx dt, which in this case will be the derivative of e to the 3t over 3 dt. Okay, the derivative of this is going to be, okay, using the chain rule, it's going to be 2 times e to the 2t over 2. The 2 cancels out, so we're going to have e to the 2t divided by the derivative of this is going to be e to the 3t. Interesting. Okay, so this is nothing but, okay, e to the 2t over e to the 3t, which is 2t minus 3t, which is negative t, so that's going to be 1 over e to the t. Okay, so now what can we do here? Well, this is just the first derivative, right? This is y prime. Okay, now we're going to find the second derivative as well. So in order to find the second derivative, we have to say that the second derivative, okay, is going to be the derivative of the derivative, right, with respect to x, dy dx. So dy prime over dt divided by, okay, dx dt. Okay, so we have to find the x dt once again, and we know that, well, that's just this, which is going to be e to the 3t. And dy prime dt, well, it's just the derivative of this with respect to t. Okay, so it's basically d of, okay, e to the negative t, right, dt, divided by dx dt, which is e to the third times t. This over here, using the chain loop, is going to be negative e to the negative t divided by e to the 3t. Of course, negative t minus 3t is 4t on the bottom, right? So that's going to be negative 1 over e to the 4th t. Okay? So this is going to be the second derivative with respect to x, right, of the function, using parametric curves. All right, so let's do question 6. Okay, so for question 6, we're going to find the area inside one loop of sine 3 theta. Okay, so this is a polar equation. And of course, we would like to know, what are the bounds of this integral, this area integral in polar coordinates. So what we're going to do is very simple. So first, we would like to see, okay, how this equation looks like, how this function looks like, right? It's almost like I think it's a flower. It's an odd numbered flower, right? So there's an odd number of petals. Usually it's the number over here, 3. If it's odd, right? If it's even, well, it's just that number times 2. So let's see how we can graph this. First we can find the period of sine 3 theta. We know that the period, okay, t is equal to 2 pi over b, in which case b is equal to 3. So that means that the period is 2 pi, okay, over 3. The period is 2 pi over 3. And we want to divide the period by 4 to see, okay, what happens in that interval from 0 to 2 pi over 3. So if we divide 2 pi over 3 over 4, we get 2 over 4 is 2. So it's 2 times 3 is 6, so it's pi over 6. Okay? So we're going to add up pi over 6 from 0 to 2 pi over 3 to see what's going on that interval. So over here we have our values of r, and we have theta. Okay, let's put a theta over here. Okay, and then r over here. So right over here we got theta equals 0. Okay, we're going to start from 0. We're going to add up pi over 6 every time until 2 pi over 3. So we got 1 pi over 6, right? We got 2 pi over 6, which is nothing but pi over 3. Okay, now 3 pi over 6 is pi over 2. 4 pi over 6 is 2 pi over 3. So this is where we stop. Okay, this is the last value, because this is what one period is going to be. This is the interval of one period of the function sine 3 theta with respect to theta. Okay, so we're going to substitute some values, right, for r equals sine 3 theta. So sine of 3 times 0 is sine of 0, which is 0, right? Sine of 3 times pi over 6, right? This is nothing but sine of pi over 2, which is 1. Sine of 3 pi over 3, which is sine of pi, which is 0. Okay, so look at that, 0 and 0. That's probably one loop, right? But let's keep going to see what happens. I don't know, let's see, sine of 3 pi over 2, that's going to be negative 1. And sine of 2 pi over 3, that should be 0 again, okay? So this over here seems to be one loop, okay? And this over here seems to be the second loop. So this is the first loop, and this is the second loop. Okay, but we're only going to find the area of one loop, right? And well, let's graph this to see what it's going to look like. So we have the xy plane, okay? But of course, we're going to integrate the polar coordinate in the Cartesian plane. So we have, the radius going outwards from the origin, right, at different angles, theta, right? So at theta is 0, which is in this direction, r is 0. So we can start with this point. At theta equals pi over 6, which is nothing but this angle over here, 1 pi over 6. The r is equal to 1. So this is about 1. Okay, let's say this is 1, which means that 1 should be around here. So this is going to be 1 point, the second point, which connects like this, should connect like this. Okay, so now at pi over 3, we have that this is 0. Pi over 3 is this angle. It's just 0. So it's actually going to come back. It's going to come back like this. Okay? And then over here at pi over 2, it's -1, which is in this direction, pi over 2, right? This is pi over 2. But if it's -1, if your r is -1, which means it's going to be in the opposite direction, right? This is pi over 2, but r is negative, it's going to be down. So it's going to be at -1 over here. So it's going to go like this. And then you're going to get something like that. Okay? Oh, it's a little iffy, but actually, yeah, no, it should be symmetrical with the y-axis. So it should be like this. Okay. So this is going to be your function. Okay? It's sine 3 theta. It has 3 loops, but we're only going to find the area of 1 loop. And remember that the area of a polar coordinate is 1/2 times the integral, okay, of r squared d theta from alpha to beta. Okay, now in this case, r is sine 3 theta. So the area is nothing but 1/2 integral. Now the lower and upper bounds will be from here to here, right? Because this is where the function meets, right? So this is going to be from 0 to pi over 3. So essentially from here, right, from pi over 3, okay, from 0 to pi over 3, which is this value over here again. So it's going to meet the value of the function once again. It's going to be equal to 0. That's going to be sine 3 theta squared d theta. Okay, so we can square that, right? No problem. And then we have that this is the area is going to be 1/2 integral from 0 to pi over 3 of that squared. Now you remember that sine squared x equals to 1 minus cosine 2x, all of that over 2, and cosine squared x, right, is going to be equal to 1 plus cosine 2x over 2. And if x in this case is 3 theta, all we have to do is multiply by 2 and put it inside the sine, the cosine. So this is nothing but, okay, 1 minus, okay, cosine of 2 times 3 theta, which is 6 theta, right? 3 times 2 is 6, divided by 2, d theta. Okay, using that identity, that trig identity. Now we can take out the half and multiply by 1/2, which is 1/4. So it's 1/4 integral from 0 to pi over 3, 1 minus cosine of 6 theta, d theta. This is an easy integral, so this is nothing but 1/4 of, this is going to be theta, and then minus, we're going to integrate cosine 6 theta using the chain rule, right? It's going to give you 1/6 sine, okay, 6 theta. All of these evaluated from 0 to pi over 3. All right, so over here we have that the area is nothing but 1/4 theta, right? Well, let's already substitute the value. So that's going to be pi over 3 over 4. So that's going to be pi over 12, okay? Pi over 12 minus 1 over 6 times 4 is 24. So it's going to be sine 6 theta, which is 6 pi over 3, which is 2 pi. Okay, divided by 24. Sine of 2 pi is 0. Okay, and then we're going to subtract the function evaluated at 0. 0 minus sine of 0, which is 0, so that's just 0. And the value of the area is pi over 12. Okay, so that's this problem. Areas with polar coordinates. And let's move on to question number 7. Oh, now we're going to enter the realm of infinite series. Okay, so for question 7, we're going to determine whether the following series are convergent or divergent. If you use a convergence or divergence test, please state which test you're using and show all work associated with applying the test and proper mathematical form. So we have that 7a. Okay, we're going to find, okay, if it converges or diverges. Right? That's all we want to know. Okay, and we're going to state which test, right? Of course. For A, we have the sum from n equals 1 to infinity of 1 over the square root of n plus n. Okay, very easy. No problem, no stress. Okay, this clearly diverges, but why? Okay, well, we're going to use a comparison test. We could compare it to 1 over the square root of n. We could compare it to 1 over n, okay? Because, you know, what's the highest power over here on the bottom? It's going to be n. So let's compare it to the highest power, okay? So suppose that a sub n is going to be 1 over the square root of n plus n. Okay, this is our original sequence inside the series. And we're going to compare it, say, okay, to 1 over n, because it's the highest power. You know, we want to see what's the behavior of these functions. Now, clearly, 1 over n, okay, because we removed something from the denominator, this function will be greater, right? As overall, it will be greater because the bottom is going to be less, which makes it larger as a whole, right? The function. So we can state, okay, that bn is greater than an, okay? So we know that from the comparison test, right? If the bigger series converges, the smaller series also converges. And also, the other part of the comparison test says that if smaller series diverges, well, bigger series diverges as well, right? But those are two different things, right? We're looking for the bigger and the smaller series. So we know what the bigger series is, and we know that it diverges clearly, right? We know that the series, the sum, right, sigma of bn, and remember that sigma bn is basically sum from 1 to infinity. This is just standard mathematical form. I just like it because it's, you know, it's sweet and simple. It's not complicated. Sigma of bn is nothing but sigma of 1 over n. And look at that. That's very nice, very famous series, right? This is this harmonic series. So which diverges, which is a divergent, right? Divergent harmonic series. Okay, don't say it's a p series with p equals 1. That's ridiculous. It's a harmonic series, okay? Now, let's do the comparison test, okay? So since bn is greater than an, right? The sum of bn is greater than an. Then we can say that if the sum of bn, okay, converges, right? Then the sum of an also converges. But that's not the case, right? That's not the case because the comparison test only allows the greater series to be convergent, not divergent. So we have to use the limit comparison test. The comparison test, direct comparison test fails. So we're going to use the limit comparison test. Now for the limit comparison test, it does not matter which series is greater, right? It doesn't matter, okay? So for the comparison test, we just got to state, oh, you could write, okay, direct comparison test fails, right? Fails. So you're going to use the limit comparison test, which is totally fine as long as you state that the direct comparison test fails, and you say that an, okay, which is going to be 1 over the square root of 1 n plus n, which is greater than 0 for now, and also bn, which is okay, going to be 1 over n, which is greater than 0, okay, for all values of okay, n, which go from, okay, which belong from, okay, the interval from 1 to infinity, right? Because that's going to be the interval of this series from 1 to infinity. Okay, so for all n from 1 to infinity, we're going to have this condition met, which is the condition of the limit comparison test. So we can go ahead, you know, this is the safe zone. So once this is met, we can say that we can take the limit of an over bn as n goes to infinity, and then compare it, you know, what's going on, what's going to happen to the behavior of this limit. This is nothing but the limit as n goes to infinity, okay, of an over bn. An in this case is 1 over the square root of n plus n. Bn is nothing but 1 over n. So if we divide it, we multiply by the reciprocal, which is n over 1. All right. Over here, we can do a little trick. We can divide by n on top and bottom. So this is nothing but the limit, right? The limit as n goes to infinity, okay, of n over n is 1 divided by root of n over n, which is 1 over root of n plus n over n, which is 1. This goes to 0 as it goes to infinity, and we have that the limit is 1. And remember that the limit states, okay, the limit comparison test states that if the limit of an over bn equals to some value c, which is greater than 0, then either both series, sum of bn and sum of an, converge or diverge. Okay, so both of them converge or diverge. And in this case, we know that bn diverges, right? So we can say that since the sum of bn diverges, then okay, the sum of an diverges as well. It diverges by the limit comparison test. Okay. So this is the answer. This simply, diverges. Okay, it's clear. It's 1 over the square root of n plus n, which the highest power is just n to the first power, right? That's just 1. All right, let's move on to part B. Okay, so for part B, we have the sum from 1 to infinity of n squared over e to the negative n plus n squared. Okay, now for this series, immediately what you want to do with every series, ideally, is to see if the limit of the, of the sequence inside the series approaches other values other than 0, right? And that's called the nth term test, right? So what happens when it's the limit of this sequence as it goes to infinity is not 0, that means it diverges, right? But if it's equal to 0, well, either diverges or converges, so it's not certain, okay? So let's take the limit as n goes to infinity of the sequence, which is n squared over e to the negative n plus n squared. We can use that old trick, divide by n squared on top and bottom, and we have that this is the limit as n approaches infinity of 1 over n squared e to the n plus n squared. I'm sorry, plus 1, which is n squared over n squared. Okay, this clearly approaches 0, right? 1 over infinity times infinity is 1 over infinity, which is 0. And well, that's just 1 over 1, right? Equals to 1, which is not equal to 0, which means that this diverges. That's it. That's the problem. Sum of an diverges, right? By the nth term, okay, nth term test. So we just found what the nth term is. If the nth term is not approaching 0, it has to diverge, okay? If it's approaching another value. Now for question 8, okay? For question 8, we're going to determine whether the following series are convergent or divergent. So again, converges or diverges. Converged or diverged. Okay, so if you use a convergence or divergence test, please state which test you're using and show a work associated with applying the test in proper mathematical form. All right, so for part A, we got the sum from n equals 1 to infinity of 1 plus cosine of n divided by n plus n squared. Okay, this is a fun one. You will see why. We also have for part B, let's put it over here. We have the sum from n equals 1 to infinity, okay, of 2 to the n plus 3 to the n, which is also very interesting, divided by n times 4 to the n. Okay, we're going to find out if it converges or diverges. All right, so here for the first series, okay, which is a very, very bad boy over here, we can use a comparison test. Well, why do I say that? Well, because, clearly the numerator, 1 plus cosine of n, is not constant, and it does not approach a clear number. It's not determined. We don't know what it's approaching, but of course, if we take the super limit, it's going to be from 0 to 2, because that's where it's going to be oscillating, right? Because what's the maximum value of cosine? Well, if the amplitude is 1, the maximum value has to be 1. Minimum value will be -1, right? Which means that 1 plus cosine of n, okay, if cosine of n is between, 1 and -1, then 1 plus cosine of n, right, we just add 1 on both sides, is going to be between 0 and 2, okay? So we're going to use something called the Squeeze Theorem. Some people call it the sandwich theorem. Either way works. And we're going to divide this by this numerator that we have in the sequence on all sides. N plus n squared divided by n plus n squared divided by n plus n squared, which is just 0, right? 0 over anything is 0, except for 0 itself, right? So what can we do here? Well, okay, we know that we're going to find the convergence or divergence of this sum. So we can take the sum in each side, right? We can take sum of 0 is less than or equal to the sum of 1 plus cosine of n divided by n plus n squared, okay, which is less than or equal to the sum of 2 over n plus n squared. Okay, this is the bigger series, smaller series. Smaller series converges, but that doesn't help us because the comparison test states, okay, that if the smaller series diverges, then the larger series diverges as well. But not the other way around. We don't know if it's, okay, if this converges, we don't know if this converges. Okay, we're not certain. Now, for this over here, okay, which looks like a convergent series, just looking at it, looking at the highest power, right? We can say it converges. We can say this converges. If this converges, then this has to converge, if the bigger series converges, right? All right, so we could use a comparison test for this. And it's like a nested comparison test because we're using a comparison test to find the divergence, the convergence or divergence of the comparison using the comparison test, right? All right, that's a mess, but it's actually very simple. So let's use the comparison test. We could even find the value of this sum, using telescoping series methods because it's actually a telescoping series. So let's use both just to be safe. Okay, so if we have that an is equal to 2 over n plus n squared, and we want to compare it to the highest power on the denominator. So saying that Vn is equal to 2 over n squared, okay, we can use the fact that this is going to be larger than this. And this clearly converges, right? So if Bn is greater than an, okay, for all values of n is greater than or equal to 1, right, then if the sum of Bn converges, which clearly does, because it's a p-series with p is greater than 1, right? P is 2 in this case. By p-series, right, p-series with p, okay, greater than 1, then sum of an converges, which is the sum of this, okay? That converges. And so, but actually, let me call this, just to, it doesn't matter actually. Let's call Cn, let's Cn equal to 1 plus cosine n over n plus n squared, just for the notation, purposes. Okay, so if this converges, okay, that means that this converges. Cn has to converge as well, right? So since, okay, the sum of 2 over n plus n squared converges, then, okay, the sum of 1 plus cosine of n divided by n plus n squared also converges, right? Converges by the comparison test. By the comparison test. And this also converges by the comparison test. But of course, the most important part is over here. So this will be the answer. But of course, if you're curious what the value of this function is, if you want to know, well, let's see. This is the sum of 2 over n plus n squared, which is nothing but the sum of 2 over n times n plus 1. Okay, this is a telescoping series. So we're going to break it up into partial fractions. This is nothing but the sum of, okay, well, let's break it up first. This is going to be 2 over n times n plus 1, okay, which is equal to a over n plus b over n plus 1. We find the least common denominator, so we have that 2 is equal to a times n plus 1, and then plus b times n, okay? So we got that a plus b equals to 0, and that 1a, right, is equal to 2. So if a is 2, b is negative 2. Okay, so we have a telescoping series that goes like this. Okay, it's the sum of 2 over n, right, minus 2 over n plus 1. Okay, so we can evaluate a few terms to see how it's going to look like from 1 to infinity, right? So at 1, we're going to get 2 minus 2 over 1 plus 1, which is 2, plus at n equals 1, right? At n equals 1 is this, right? At n equals 2, we're going to have 2 over 2 minus 2 over 2 plus 1, which is 3, plus we're going to have 2/3, right, at n equals 3, and then we're going to have minus, okay, minus, we're going to have 2 over 3 plus 1, which is 4, which is 1/2, plus dot, 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 plus 2 over n minus 2 over n plus 1. Okay? And what's going to happen over here is that this cancels out with this cancels out with this cancels out with the next term, and at last this cancels out with the previous term. Okay? So we have that the sum Sn is equal to, okay, this value 2, which is left, minus the last term, which is 2 over n plus 1. So if we take the limit of the series and it goes to infinity, we can find the value of the series. So I'll take the limit as n goes to infinity of Sn, which is just the limit as n goes to infinity, okay, of 2, right, 2 minus 2 over n plus 1. And that's nothing but 2, okay, so the value of this series, this sum, is 2, which converges, right? So this is going to be problem 8, 8. Okay, so for part B, we have the sum, okay, we got the sum from 1 to infinity, from n equals 1 to infinity, of, I think I wrote it over there and I just erased it, yeah, because there was not enough space, of 2 to the n plus 3 to the n, all of that divided by n times 4 to the n. Okay, for this, what I did was a little bit unorthodox, it was like a two-step problem. But no problem. I think we can use a comparison test. We can compare this given that an, okay, given that an is equal to 2 to the n plus 3 to the n, divided by n times 4 to the n. We can compare it to bn, which is the highest power on the numerator, okay, 3 to the n, divided by n, okay, times 4 to the n. And, we can use the limit comparison test. The conditions for the limit comparison test are so that an is greater than 0 and bn greater than 0, okay, for all values of n which belong to the interval from, okay, 1 included to infinity. All right, so we're going to take the limit now that that condition is met. We're going to take the limit of an over bn as n goes to infinity, right? So we're going to have nothing but the limit as n goes to infinity of an, which is 2 to the n, plus 3 to the n, divided by n times 4 to the n, divided by 3 to the n, divided by, 4n times 4 to the n, which is basically multiplied by the reciprocal. So it's nothing but multiplied by n times 4 to the n over 3 to the n. This cancels out. We just take the limit. And if we do that, we distribute the 3 to the n on the bottom on each term on the numerator. We're going to get the limit of 2 to the n over 3 to the n plus 3 to the n over 3 to the n as n goes to infinity. This over here is 1. And this over here, as n goes to infinity, okay, because it's a geometric series, right, just approaches 0. Okay, so that means that the limit is equal to 1, which is some value c that's greater than 0, which means that either the sum, both sums an and bn converge or diverge, okay, provided that we know the convergence of bn, right? So does it converge or does it diverge? It's not very clear, right? But we can use another test, convergence test. We can use the root test, okay? Use the root test to find the convergence of bn, okay? So if bn, okay, the absolute value of bn is equal to 3 to the n over n times 4 to the n, then take the limit, okay, the limit as n goes to infinity of the nth root of the absolute value of bn, which is nothing but 3 to the n divided by n times 4 to the n, okay? Look at this. This n cancels out with this n, and this n cancels out with that n, and we're going to be left with 3/4 divided by the nth root of n. Okay, and don't forget to place the limit as n goes to infinity. Now the limit as n goes to infinity of the nth root of n is just 1. Okay, this approaches 1. It's just, a basic limit, which means that the entire limit approaches 3/4. Okay, which is some value c, which is greater than, I'm sorry, in this case, we're using the root test. So we're trying to see if this is going to approach some value rho, okay, which is, in this case, less than 1, which means that it converges, okay? So sum of bn converges, it converges by the root test, okay? And since the sum of bn converges, then the sum of an has to converge by the limit comparison test, right? So then sum of an converges by the limit comparison test. Okay, so that's the answer to part B, 8b.